Hello student, welcome back to the lecture series over the DC circuits. In the last lecture, we have seen how to solve the electrical network problems, simple electrical network problems by using the Maxwell's loop method, Maxwell's mesh analysis method. Now today we will see one more theorem, one of the important theorem from the means electrical engineering point of view as well as exam point of view, because definitely one question will arise on this theorem. The name of this theorem is the superposition theorem, and this theorem is useful for uh, analysis of a simple network. Okay, along with the KCL, KVL means Kirchhoff's law, this theorem is equally important, and all the electrical engineers, even the students, those are going to use the electrical circuit, they must know how to apply the superposition theorem. Theorem is very simple, and here is the statement of superposition theorem. In a linear bilateral DC network containing more than one generators or source of EMF, the current which flows at any point is the sum of all the currents which would flow at that point if each generators were considered separately, and all the other generators replaced for the time being by resistances equal to their internal resistances. Okay, then question arises when to use the superposition theorem. Superposition theorem is applicable if the circuit contains more than one EMF sources. Now, EMF sources means, for example, in the last example also we have seen that there are two EMF sources, means batteries. Here 6 volt battery is there, 12 volt battery is there. Then we can apply the superposition theorem. If single battery is there, then no need to use the superposition theorem. Directly you can find out the current as well as voltages in any branch by using the Kirchhoff's laws, Kirchhoff's current laws as well as the Kirchhoff's voltage laws. But if there are the multiple sources are there, now here we are using only the two sources. Here also we can solve the example by using the only the Kirchhoff's voltage laws. But in reality, only two sources are not there. There may be the 10 sources, 15 sources, more than that sources. In that case, using the Kirchhoff's voltage laws is become tedious. Okay, difficult. Then alternate way is to use the superposition theorem. But for simplicity, we'll go for only two sources. Once you understand how to apply the superposition theorem, then how many sources are there, that is not a problem. Okay. Now, as the statement means itself understandable. What is the meaning of that? Means if there are multiple sources are there, then first of all we have to replace the other sources by their equivalent resistances. Other sources means, for example, if we are using the voltage source, then we have to replace that voltage source by the short circuit. Okay, and if there are the current source, then we have to replace it by the open source. Okay, because the equivalent resistance, ideally equivalent resistance of voltage source is 0, and equivalent resistance of a ideal equivalent resistance of a current source should be infinity. Then how to apply? If two sources are there, then one source we have to make means we have to replace that source by using its internal resistance. Now here the second source is voltage source, then we have to replace this voltage source by its internal resistance, that is 0. Okay, ideal voltage source is 0. If nothing is given in the example, then we have to replace the voltage source by 0. If in the example if they have given the value, that may be 1 ohm, 2 ohm, 3 ohm, then we have to replace that voltage source by its equivalent resistance. Now here equivalent resistance, internal resistance is given here, that is a 1 ohm. Then we have to replace this voltage source by 1 ohm whenever we have to remove it. Here also this source is shown the equivalent resistance as a 0.5 ohm. Okay, now what to do next? First of all, now one by one we have to go on replacing. Now timing we will assume that this 12 ohm we have to replace by 1 ohm resistance, now as shown in the figure B. Here 12 volt is not shown and only 1 ohm its equivalent resistance is shown, and here only one EMF source we have kept as it is. Then in this case we have to find out the current in each branch using the Kirchhoff's voltage law, you can apply any voltage law, any law which we have learned earlier. Means you can use the Kirchhoff's laws using the arrow or using the mesh analysis. Now, once the current is obtained, now the current, because of a single source, we have to give name as a I means dash. Use the symbol dash. For example, the current flowing through this 2.5 ohm resistance, we will give the name as a I1 dash. Through 2 ohm I2 dash, 1 ohm again I2 dash, and here is the I dash. Now I dash means, now as if our assumed direction is in this way and this direction is in this way, then what will be the value of I will be equal to this I dash is equal to I1 dash plus minus I2 dash. Okay, I1 dash minus I2 dash. This is by using the Kirchhoff's current law. Means at this point, incoming current is the I1, outgoing current is the I2 dash. Therefore, I1 plus I dash is equal to I2 dash. Okay. Similarly, now once these current values are known to you, then now we have to replace the previous EMF, that is a 12 volt. Now here we have to remove the another voltage source, that is another voltage source is the 6 ohm. Now here you can see the diagram for that. Here 12 volt is kept as it is with 1 ohm resistance. Then here we have to replace the previous EMF source by its equivalent resistance, that is the 0.5 ohm. Okay, then again you have to find out the current through these branches. Then now as here 12 volt is applied, now here you can see that the directions, arrow directions, we have reverse, and whatever current you will find, now you have to give the name, means you have to denote it as a double dash. For example, current through 2 ohm will be I2 double dash, current through 2.5 will be I1 double dash, current through 6 ohm will be I double dash. Then what is the procedure? The procedure which just we have discussed, we will again learn using the step by step. The procedure for using this theorem to solve the DC network is as under: select one source in the circuit and replace all other ideal sources by short circuit and ideal current source by open circuit, as we have discussed. Determine the voltage across or current through the desired element or branch due to single source selected in step 1. Repeat the above two steps for each of the remaining source. Algebraically add all the voltages across or current through the algebraic element under the consideration. The sum is the actual voltage across or current through the element branch when all the sources are acting simultaneously. This theorem is called superposition because we superpose or algebraically add the components, that is current or voltages, due to each independent source acting alone to obtain the total current in or voltage across a circuit element. Now just we will see an example, uh, just by giving the values in earlier circuit, means in this circuit. Now in the circuit, let the battery EMF be 6 volt and 12 volt. Their internal resistance is 0.5 ohm and 1 ohm. The values of other resistances are indicated by the different current flowing in the branch and voltage across 6 ohm resistance. Means we have to find out I1, I2, I3 as well as the current flowing through 6 ohm. Means this I value we have to find out. I as well as the voltage across it. Then now as in the figure B, 12 volt battery has been removed through its internal resistance of 1 ohm. The various current can found by applying the Ohm's law. It has been seen that there are two parallel paths between A and B having the resistance of 6 ohm and 2 plus 3, that is 3 ohm. Equivalent resistance is equal to 3 in parallel with the 6 ohm, that is the 2 ohm. Okay, now here you can see that 6, this 6 in parallel with 3. 6 in parallel with 3, then this value comes out to be 2 ohm. Now if we add this 2 ohm with the 0.5 resistance of 12 ohm 12 volt resistance, then plus 2 2 is the equivalent resistance 2.5. Here you can see that this is the 2.5, then equivalent resistance is the 2 ohm and this 0.5. Then finally we will get the total value. Therefore I1 dash is equal to 6.5 is equal to 1.2 ampere. This current divides at point A inversely in the ratio of the resistance to parallel path. Then I1 dash by using the voltage divider network. Now voltage divider network we have seen earlier. As per the voltage divider rule, this I dash is equal to incoming current, that is 1.3 multiplied by the resistance across which we have to find out the current, that is 3 divided by the total resistance in the parallel. It comes out to be 0.4 ampere. Similarly, the I2 dash is equal to 1.2 multiplied by 6 divided by 9. It comes out to be 0.8 ampere. Then once these two currents means are known to us, then it's time to replace the another battery. Okay, means replace this another battery and remove the batteries for which we have done the calculations. Then the same figure is shown in figure C. We can see that in figure C the 12 volt 0.5 ohm resistance, internal resistance we have replaced. Here is the figure C, and here 12 volt batteries used. Now similarly, in this case also we can find out I2. In figure C, 6 volt battery has been removed, but not its internal resistance. The various current and their directions are as shown. The equivalent resistance to the left point A and B is 3 parallel with the 6. It comes out to be 2 ohm. Total resistance is equal to 5 ohm. Then by using this calculation we can find out the I2 double dash is equal to 2.4 ampere. Then at point A this current is divided into two parts. Therefore I dash is equal to zero point 0.8 ampere. I1 double dash is equal to 1.6 ampere. Now but these are not the actual current, because actual current as per the superposition theorem is nothing but the algebraic sum of the current which we have obtained by using the individual EMF sources and replacing the other EMF sources by their equivalent resistances. Therefore, as per the superposition theorem, I1 means current flowing through uh, this I1 means this current. Now this current, what will be the value of this current? I1 dash current is going I1 dash plus I1 double dash. But now as the I1 double dash direction is reverse, therefore we have to use the negative sign. Means your I1 is equal to I1 dash minus I1 double dash, and same is taken here. Here you can see that I1 dash minus I1 double dash, and it comes out to be minus 0.4 ampere. Means again minus 0.4 means the direction which we assumed earlier for I1 is incorrect, and we have to use the opposite direction, means this direction. This we have assumed that I1 is flowing in this way, but actually I1 is flowing like this one. Okay, again we will go back. Then I2 also, I2 we can calculate like I2 double dash minus I2 dash is equal to 2.4 minus 0.8, and it comes out to be 1.6 ampere. Then this is for I2. I2 is positive, means our assumed direction is correct. Similarly, I is the current flowing through 6 ohm resistance, and it comes out to be I dash plus I double dash, and the value is 1.2 ampere. The voltage drop across 6 ohm resistance is 6 multiplied by 1.2. Now how we have calculated the current flowing through 6 ohm resistance is 1.2. Current multiplied by resistance is nothing but the voltage. In this way we can find out the current in any branch, voltage in any branch, using the easily using the superposition theorem. Okay, I think all of you have understood how to find out the current, voltage, that is known as the analysis of the circuit using the superposition theorem. Okay, in the next lecture we will see one more important theorem, that is the Thevenin's theorem, which comes under the category of the network reduction technique. Okay, we will see its use. Till the next video, Goodbye. Take care.